Okay. I think, I think, yeah, everything seems good to go now. Okay. Good day, everybody. Hope you're doing well wherever you are. And in our first episode of Rust for C, C++ programmers, I made a simple arena implementation where we allocate a big block of memory and we divvy up that block of memory into smaller buffers, and those buffers will be managed by arenas. And those arenas are then passed throughout our application and used by our code to allocate memory. The implementation is pretty simple at the moment, and mostly served as a demonstration to show like how we use unsafe code in Rust. As we can see, we already have a few unsafe blocks here, and that's completely fine. There's no problem with that. But one thing that I think we should do is that we should make an effort to probably making our code a little bit more secure, because there are ways of writing valid Rust code that the compiler will compile just fine, but will create a seg fault. So let me, an example. In this case over here, this is an arbitrary example to just get the point across. But I think what's important and what you should take away is the dynamic that we can observe and that we can see in other places as well. So in this case, we have a block that's in its own scope, and that scope is going to return an arena created from that block. The problem is that once we're outside of that scope, the block is going to run its drop function and unmap that memory space. We don't want that, obviously, because if we unmap that memory space, then the arena that's backed by that memory space won't work properly anymore. So this, as we can see, like my LSP isn't showing any errors. And if we were to build this, everything runs just fine with no errors. And if we run it, we see that we get a seg fault. So ideally, we don't want this in our code, right? Crashing, a code that crashes usually isn't what we want, unless that is how we decide that like we want to deal with bugs. But this is a bug that we want to avoid in all cases whatsoever. And I think a thing that a lot of C programmers the misconception about Rust is that like the borrow checker is very strict, and it can be when you're going from unsafe code to unsafe code. Whereas the experience in my own experience is that when you're going from unsafe to safe, you're kind of adding more details to your code so that the compiler can come in and like already make checks for you that sometimes if you're not paying attention, like you don't realize that like, oh yeah, like this is backed by something and I forgot this goes out of scope, but this reference is still valid, and then bam, we blow things up. It's very easy to forget. We do it all the time. So I would like this to be a compile time error. How can we go about doing that? So let's go back to our implementation real quick. And one of the ways that we can add more information for the compiler to be able to recognize that this is an error is by using markers. In Rust, there's a module called marker, and we have the main marker that's used is phantom data. There's some experimental markers that are available in nightly Rust, but the one that's most often used is phantom data. And what phantom data does is that you create a field on your struct that will be uh, a phantom data marker, and Rust will then treat that struct as if it owns the type that phantom data is over. So that sounds confusing, but I think in practice you'll see that it's much simpler. So what we would like is that this arena is tied to our memory block. And how we express that would be through what Rust calls lifetimes. Now, most people have seen like the tick A like this, and I personally think that like these one-letter lifetimes that you usually see in a lot of code is a pretty bad practice. I think we should be a lot more explicit and give them names, just so that it's clear to the user what this lifetime is tying to. So I'm going to give this lifetime the name block, so that I know that this arena is tied to a block. And at the moment we have an error because this lifetime is unused. Bummer, just about to use it. So we're going to create the marker. That's going to be phantom data. And here we add the type information for what we want this arena to act like it owns. So we want this arena to act like it owns a reference to the memory block, even though it doesn't. So arena, and we also want it to, so it wants to act as if it has a reference to a mutable. Oh wait, for this to be block. And we're gonna have to make a few updates to our code first, since we've already added this type information. Rust understands now that this implementation block needs some more details. So let me add that. In the case of this tick underline, it just elides the lifetime, and so we don't have to keep on repeating code everywhere. And here, just copy this. And we also want to add this lifetime over here to our era implementation. In the case over here, like we're getting a small a warning that we aren't using this lifetime, we can tie it over here, just so people understand that where the lifetime is being applied. Actually, oh no, yeah, we don't need to put there. Don't worry about that. And we have one other place to modify, which is in our memory block implementation. The arena function now needs to have a lifetime added to it so that it knows that the return from this function scopes the arena that it returns. And now with that simple change, if we go back to our example, we can see now that we're already getting a few errors. So block does not live long enough. And I'm sure if you tried writing Rust before, you've come across this error, but I think it's nice to come at it from the other side, where we're purposely making this, we're making it so our code makes this error occur, and not having to like fight with the bar checker and make it so this error stops happening. We're seeing the utility of like why this error happens, instead of like feeling like we're going up against a wall and like trying to do something that we know we can do, but that Rust isn't preventing us. Now, I hope like people can appreciate a little bit more how Rust gives us this flexibility to like go between safe and unsafe. and how you can control it. And the only problem now is that if I were to run my tests don't compile anymore. And let me open up the test just to show. You can see now that we are getting errors over here as well. And in this case, we're trying to borrow block offset as immutable, but over here we've already borrowed it as mutable because this block's arena function is tying that arena to the block because the arena acts as if it has a mutable reference to that. And if you have a mutable reference to something, you can have immutable references to it as well. You can only have one or the other. They're mutually exclusive. You can either have many immutable aliases, or you can have one mutable reference, which allows you to change the contents of what's in that reference. The way that I like to remember it is like the way that I like to remember it is sort of like the way that, for example, I have various different kinds of aliases. I'm a son to my mother. I'm a brother to my sister. I'm a husband to my wife, and I'm a father to my baby daughter. I have a bunch of different aliases that people can refer to me as. But in some moment in my life, somebody gets mutable access to me, and then like my relationships change as a result of that mutable access. What I mean by that is like I was my mother's son, I was my sister's brother, and before my wife became my wife, she was my girlfriend, and then before that, she was just somebody that we saw occasionally, and then things change, right? And every time that every step in our relationship that we took, it was another change, and as a result of that change, everybody else needs to now like get an update as well, because like for my sister, the brother that she had before isn't the brother that she had after, right? Like there's something different. And the same thing also happens with our code, where it's like if you have immutable references to a space of memory, and then somebody were to change that space of memory, all of those references now are invalid because people were making references under the expectation that nothing changed while they had that reference. And Rust, with its borrow checker, prevents us from doing either one of those at the same time. It's possible to do so with unsafe and understanding how things work behind the scenes, but usually we don't want to do that. But now I don't like these errors. Like I would like to maintain this compile time error, but not have these because they're completely different scenarios. Like in this case, what's happening is that I create a block, I create an arena from that block, and then I consult both to see what's going on. But since it acts as if it has a mutable reference to that block, I can't check what's in it because technically, if I have mutable access, an immutable alias to that same spot of memory now is invalid. But I know that it isn't. So Rust is kind of overstepping what I wanted to do right now. And thankfully, we have a way to go about fixing that. In this other scenario as well down here, we can see that like the error over here is that like I'm allocating more than one arena up front. And I feel like that's an interesting, like I want to maintain that functionality. I would like to be able to create multiple arenas up front and then pass them around, and then they'll be used when they're used. I don't want it so that I have to create arena, use it, have it go out of the scope for me to create another one. In some scenarios, that might be what you want, but in this case, I don't want that. So what can we do to solve that problem? And what Rust offers us is what's called interior mutability. Interior mutability is offered to us through the cell data structure. And a cell is a data structure that represents a shared mutable location in memory. And what that allows us to do is that you can pass immutable references to a cell, and through that, and because a cell is a shared mutable location, you can also change the contents of that cell through an immutable reference. You don't need mutable access to change the contents of a cell. And that's because what the cell does is that it only like switches the contents. You give it a new thing to put inside of the cell, it takes the old thing out and puts a new thing in. And that could be problematic in a multi-thread context, because in multi-thread code, you would not want that. You wouldn't want multiple threads to have that sort of access to a location in memory, and that would have to be facilitated through like a spin lock, a mutex, or whatever concurrency primitive that you want to use to like to mediate that access. But where is it? But in our scenario, what we want to do is only single threaded, and thankfully also Rust makes cell not have the sync and send the sync and send traits, which are traits that Rust automatically adds to a data type if it can be moved around threads without any data contention. I'm sure I could explain that better, but I can clear that up in another episode. But since we're not talking about multi-threaded code at the moment, I'm going to say that for another episode. But since we're in a single thread context, what we're about to do isn't a problem. But I do want to just make a point of how it could be a problem. But thankfully, with Rust's type system, if you add any sort of field that is a cell into your struct, that data structure now can't be used in multi-threaded code. You're going to have to do something else to make it so you can use it in multi-threaded code. So yeah, let's import cell. And what we want to do now is we have offset over here, and the only, like during the life of a memory block, the only thing that changes throughout the lifetime of this data structure is the offset. The buffer and capacity are completely static throughout its whole entire lifetime, because we don't expect to reallocate this and like keep on or in like shrinking or increasing our buffer. And in the same case of the buffer, it has to maintain this address so that we can unmap it correctly. So what we want to do now is change this cell into a usize into a cell usize. And for those of you who are wondering, like what's the cost of using a cell? Thankfully, like in the memory layout, a usize and a cell of a usize are the exact same size. The only difference is how the type system sees them. For more details, I suggest reading the cell module documentation. It goes into a lot more of the details, and also the other data structures inside of the cell, which are rough cell and one cell. There's also, I think, is lazy cell also in there yet? Lazy cell might not be in the standard library. I might be confusing it with something else, but I know that rough cell and one cell are. But now we're working with just a normal cell. And a cell just allows us to have a mutable location in something that is supposed to be immutable. And let me make a few changes to our code. And now over here, for example, like in this arena buffer function, since we can mutate the contents of the cell through an immutable reference, we don't need to add this anymore. So We only need an immutable reference to self now. And also, this will not be returning an immutable slice. So we'll just be returning an immutable alias. We should also update our arena function as well. And our from slice it in the arena implementation. Since we are not accepting an immutable slice anymore, we remove this. And since we don't have a mutable reference to that slice, we can't use asmute pointer because asmute pointer needs this slice to be a mutable reference. So what we can do is that we can is this correct? Yeah, we can get a constant pointer and then cast that into a mutable pointer of so yeah, there's nothing that stops us from casting between a constant and mutable pointer. And with that, let me just check if everything's right. I think I just need to make a few updates to our test now. And since this offset is going to be inside of a cell, and you have to use a function to get what's inside of a cell, I would rather create an interface in our structure that facilitates that instead of calling offset.get everywhere. You can just call a function on that memory block that we call offset. So let's add that. And itself, offset. And now I just need to update our code to replace that offset, all to make it call the function. Let me just check if there are any more things that we need to change. Yes, and over here, now that we don't need a mutable reference to change the inside of the memory block, we don't need to declare this as a mutable block. So let's remove these. We can remove this test, which is just the use after free that I made, that I demonstrated in the other example. So now we can see that like we aren't getting any errors anymore. And if we go to our example, we still get this error. And this is one of the things that I like about Rust, which is that I think a lot of people fight with the borrow checker a lot, and I have as well. Everybody has, don't worry. But but I think a lot of people don't understand that like you also have a lot more control over the borrow checker than you initially believe that you do. And Rust gives us a lot of tools to be able to circumvent it or not circumvent it, but play around with the rules. It's like, I think the fun thing is that like Rust gives us a lot of people, like a lot of people don't like Rust because they feel like they have to follow too many rules and that like they just want to do the thing. But the thing about rules is that like once you learn them, you can also learn how to break them. And we can see like now that we can do what's, correct me if I'm wrong, but I think this would be like an example of what we would call reification in computer science. And that doesn't mean that you get turned into a blue-haired schizoid anime girl. That just means that we've brought an abstract concept into a concrete and into the concrete. So we have this notion of like this block is tied, well, no, this arena is tied to this block. And initially we couldn't like make that explicit. We couldn't make that something that like the that our languages recognizes as something that's happening. But through a few simple modifications to our code, you can see now that like now we brought it from an abstract into an idea into something that the compiler understands and now can enforce. And now you can now you're saving yourself from a headache in the future, because when haven't we passed around references without thinking about it and then forgot that, oh wait, this was deallocated, I didn't realize it, and now we have a bunch of references that are accessing something that's been allocated. It happens to the best of us, and the times that it happens, it's very frustrating to figure out where it's coming from. And thankfully, we have a tool that allows us to be able to express these ideas and make compile time errors. Now I don't have to worry about this potentially happening in my code, because the LSP will show me before it ever happens. Because in this example, like we can obviously see, like I would never write this code. This code doesn't really make sense to write, but these bugs happen across modules, and it's good now that we have a way for us to be able to check this and for us to be able to see it across modules. Because if this were happening across files, this error would still show up, and I wouldn't have to remember all that context of like the whole entire system that I intend to make to be able to understand, like, oh yeah, like this is referencing something back over there, and that's doing this, and blah blah blah, and then bam, it blows up because I forgot something. Now it's compile time. And that's one of the great advantages of Rust. We can use the type system to make things that previously were runtime errors that we would only discover if like we wrote code improperly and then saw it during execution, into things that no, like I can now tie this arena to this memory block. And because of that relationship, the compiler can now figure out that like, you're using this incorrectly. Thank you, compiler. Like, thank you for saving me from myself. Because I do a lot of dumb things, unfortunately. So let's try to run that example. We can see now that we can't, it won't let us compile. But if we were to run our test, actually it still won't compile because we have to comment this code out now for our test compile. And now our test compile with no problem, while still maintaining a very intuitive interface. So this is going to be episode 2. For the third episode, I'm still thinking of one. I think for the third episode, we're going to go through a few data structure implementations using what we use in our arena application. Yeah, so thank you for watching, everybody. Make sure to like, comment, and subscribe. And if you have any questions, feel free to comment. I want to interact with the community and see what you guys think. And also, if like you're seeing any bugs, feel free to point them out. Although in some of them, I might be leaving some there as a teaching experience later. So I don't know where they are yet, but once I find them, it's going to be a teaching experience. Don't worry about it. Yeah. Have a great day, everybody. Peace.